Okay, welcome to day 2. A couple of quick reminders. I have PLC 1 posted as a quiz style thing, so you're going to take a couple of, answer a couple of questions, and the last one is a write down an explanation type. So those are Friday. That's going to be a recurring theme, right? Every week we're going to have one of these due, and it's going to be due Friday by the end of the day, 11:59. I have to put 11:59 now because I can't put midnight, because if it's midnight, it's the next day. Homework 1 I posted yesterday, and that's going to be due on Tuesday, which is the Tuesday after next Tuesday. So say 2 weeks from yesterday. It's going to encompass the stuff from this week and then the stuff from next week. And then it's going to be due. Every time we have homework due, there's going to be a quiz associated with it. So whenever you're turning homework in, expect to take a quiz that same day, okay? Alrighty, so in the meantime, I'm planning on a more conceptual quiz to be given probably around this time next week. So take a look for that. I'm thinking probably Wednesday next week. It's going to be a conceptual quiz, which means I'm not expecting any calculations Wednesday next week. I'll put a question mark. If that changes, I will obviously let you know. Okay. Oh, and that means I should put this here plus. On that day, we'll have plus quiz number 1. So that's plus homework quiz number 1. Looks like green's not showing up too. Okay. All right. So we left off last time with the ray diagram of a converging mirror. So let's pick that one up, especially given that the rays that I drew were of a particular type. So I brought my mirror in again today. So we'll have bit of chance to take a look at this. I was unhappy with how this showed up last time, so I'm not expecting anything really different. But what I have here is a curved mirror. It's silvered on both sides, so one side you get the converging effect. Let's see, where do I hold it? Right there. One side you get the converging effect, one side you get the diverging effect. Okay, so it looks kind of like that, or like that. Okay. If I take a look at the converging side, I'll do it from this side because that's the way we go. Okay, I'm trying to show you that it's not really showing super well. You know what? I know what it is. It's the laser's too intense for the camera. Camera's automatically correcting because of the intensity. All right, so right there you can see, at least you can see it going in, but you can't see it leaving. Okay. Well. The cool thing is, I guess I can just draw that. So we'll go back to the converging mirror. And we'll pick out our axis of symmetry, which say is going to be about here. And I'll put an object on there. Right there. Now, I talked a little bit about the focal point last time as being the place where parallel rays to this axis, rays that come in parallel with this axis, where those rays will converge, is called the focal point. Okay, so it turns out, let's say that the focal point is here. I'm going to call it F. Like that. It's a little small, sorry, but that is F right next to that dot. And it turns out that's also a geometric property of the curvature of the mirror. So once you have the mirror's curvature, Okay, once you've established how curved the mirror is, it's like you can't change that curvature, which means you're not changing the focal length. The focal length is related to the radius. In fact, for a spherical mirror like this, what we find is that the focal point is half the distance of the radius. So we find here that the focal length, point F, is equal to 1/2 of the radius that makes the circle, right? Like where you would put the point of your compass and then you would scribe this circle out like this. That point is the center of the circle, right? So that distance would be the radius. And the focal point is half that radius. So that's a property of the geometry of the circle that is, or the sphere, the spherical arc that is making the mirror. So going back to what I was saying last time, parallel incoming rays, and I leave off the words when I say parallel, I am always talking about rays that are parallel with the optic axis here. So if I say parallel incoming rays, what I mean is that they're coming in this case, since I've drawn the axis horizontally, I mean horizontal rays coming in like this. Okay? So I'm going to pick one ray that's coming off the top of this object, like I did last time. It's going to come in straight. Whoa. All right, like that. It's going to come in parallel. It's going to go out through the focal point, like that. And I don't need to worry about measuring the angle of incidence and the angle of reflection, because I'm guaranteed that if it's coming in parallel, then it's leaving through the focal point. And I got quite a lot of ink dripping here. Okay, that was a pretty, pen got a little excited. Okay, all right. So I don't need to measure, I don't need to go over here, drop a normal, and measure angles. I'm guaranteed that my parallel incoming ray will leave through the focal point, because that's the property of the geometry of the system. Okay, so I'll call this ray number 1. What I'm going to say is incident. It's incident on the mirror, parallel to the axis, and it leaves through the focal point. Okay. So I'll call that ray number 1. I'm going to now choose ray number 2, which is going to be the same one as I did last time, which is the one that hits right here at the intersection of the symmetry axis with the mirror. Now, at that point, the normal is the axis. Right? Because at that point the tangent is vertical, so the normal is horizontal, and it is the axis, and therefore I don't need to worry about obeying the law of well, I do need to worry about obeying the law of reflection because it's a law, but all I need to know is that if I come in and I hit that point from the top of the object, all I got to do is go out at that exact same angle, and we'll be all set. So I'm guaranteed that'll work. Let me try doing this a little bit less colorless here. We're going to go right in about here. Okay, like so. All right, so that's the incoming and the outgoing, and I have got a crossing here just as I did last time, which is where the image is going to be formed. So the top of the arrow should be right about there, and the arrow should be something like that. Of course, I drew an arrow to indicate the arrow, so let me not do that. The image is right there. The image is this thing, not this thing. The image is that thing right there. I want to introduce you all to ray number 2. Let me write that down. And then we'll go and hit ray number 3. It is incident at the, I don't know, the point where the symmetry axis crosses the mirror. Maybe I'll call that the vertex point. Can I do that? Incident at the vertex point. It's the crossing of the mirror plus the axis, and it leaves at that same angle. Okay, ray number 3 is going to be basically the exact opposite of ray number 1. So instead of being incident parallel and then leaving through the focal point, ray number 3 is incident through the focal point and leaves parallel due to the reversibility of light situation. I'm going to take this object and I'm going to, instead of having it here, I'm going to put it right here where the image is. And now I'm going to trace the rays from the object, which is now here, upside down relative to what it was, and it's moved here, and I maybe have I've pulled it out a little bit like that, made it a little bit longer, and so here I'm going to look at the rays, and I'm going to do the exact same thing, right? If I thought about the rays coming in, well, ray number 2 is easy. It's just going to be totally reversible as to the path that it was, the path that it had here, right? It's going to be the exact same path. Ray number 1, I can imagine, right, is now basically ray number 3. It's going to be incident from the focal point and then leaving parallel in opposition to coming in incident parallel leaving through the focal point. So the light paths themselves are reversible, okay? So ray number 3 is incident through the focal point. And I'm going to say it's either through the focal point or from the focal point. And the reason I'm putting that in is because of something we'll talk about in about 30 minutes. Okay, so it's incident through or from the focal point. And then it leaves it leaves parallel with the axis. Okay. All right. That one I haven't drawn here. I guess I will draw it here, and then we'll do what I wanted to do. Well, actually, you know what? Yeah, we're good. I'll draw it here. I'm going to put the light beam through the focal point here. It's going to come down there, and it's going to come, hit, and come out parallel. But you'll see that it's not very good at reproducing where the other two. So in this case, less data is sometimes more usable, or at least it makes you feel a little better about the drawing that you're doing. Yeah, I will say this one is very curvy downwards, and I have not been very precise about the straightness of these rays. But nonetheless, in a well-sketched, which this is not, in a well-sketched ray diagram, all three of these would meet at the same point. Or at least close, right? That's what you'd hope for. Okay. So those are the three rays. Great news about the three rays. These rays are usable for every type of mirror. Well, I mean, not a plane mirror. There's no focal point. Okay? Fine. But for a converging and for a diverging mirror, they will work. Then, next week, we're going to go to lenses. We're going to use the exact same three rays. All right? So once you get used to thinking about where they are and what they're doing, they're going to be very useful because we just keep using them. Okay. That being said, I want to now go to a different ray diagram for the converging mirror. Okay. This is one in which I take the object, which instead of now being outside the focal point, I'm going to slide it to inside the focal point, and we're going to see what happens. Let's see here. Where can we do that? I guess I'm going to do it right here. Okay, so that's the end of this one. Alrighty. So we will do converging mirror again. Now this is going to be object within the focal point. Oops, object. Within F. All right, so I've got my converging mirror, I've got my axis, I am going to put in a focal point and an object. Now I'm going to kind of exaggerate this a little bit, or say zoom in a little bit. I'm going to put the focal point way over here. I'm going to put the focal point way over here just so I have room to do the ray diagrams. I'm going to put the object right in here. All right, and apologies for its smallness, but I do need to kind of have it a little bit small in order to make this diagram work out, but hopefully you can see that reasonably well. I will darken in the focal point. It's right there. Okay, okay, good. So my object here is at a distance away from the mirror, and that distance is less than the focal point. All right. Now we're going to do the same exact thing that we did before. We're going to do a ray coming from the top of the object and going in. A ray coming from the top of the object, incident parallel, leaving through the focal point. This is going to get a little tight on this one, but we're going to have to. I'm going to have to make it work. Actually, instead of doing that one, that one's just too thick. Let me do this one. Okay, so parallel incoming ray. I do feel like I could use a good straight edge though. Let's see if I have something. How about this? I gotta remember to start bringing in a meter stick or something. You know what? I'm gonna go grab one right now. Okay. So I'm going to take this and, this is way better. Now we're cooking with gas. All right, here we go. We're going to do this. All right, so it's going to come from the mirror. It's going to go through the focal point. It's going to look like that right there. I'm going to take a little bit of care and going that way. Just so that my ink doesn't run, I didn't put it right over the object. But you can see that ray, I think. You can see that ray. That's ray 1. Comes from the object, parallel with the axis, out through the focal point. I'm going to check out ray number 2. Actually, you know what? I'm going to skip to ray number 3 for a sec, because we did ray number 2 already for one. It's a boring ray. Let's check out ray number 3. Ray number 3 is incident through the focal point, but how can that be? In contrast to the last ray diagram I had, it was very simple because the object was here, the focal point was here, and the ray went down, right? So no problem. In this case, though, the focal point is behind the object. So that's why I wrote from. I guess 30 minutes was too long of an estimate. I thought maybe I'd do this later. So instead of going through the focal point, we assume that it came from the focal point. So I can pick a ray of light, which is leaving the top of this object, and going at the exact angle as if it had come like from the focal point, as if it's on that line from the focal point. Remember, these objects emit an infinity of rays in an infinity of directions. So we're not cheating. Every ray is possible. This one just happens to be on the line that connects the top of the object with the focal point, like this. Okay? And when I do that, I find, right, so it's going up like that, it's going to go that way. Okay? There's a ray of light that comes off the object that's going that way. And it's on the line that connects the focal point with the top of the object. Okay? Just like it was in the previous ray diagram, connecting the top of the object with the focal point, but that would just look like it was much more straightforward. Well, this is just kind of backwards. But I'm still guaranteed, because it's on that line from the focal point, it comes out parallel with the axis. I'm still guaranteed that. So this works really well. I'm going to take this thing here, we're going to run it straight parallel with the axis, and off it goes. Okay, it goes that way. Like that. Okay? And now you can see something interesting. So our converging mirror is not converging the light rays. Perhaps it's a poor name, but it's the one I stick with. Right? This thing here, this ray here, I'm just gonna, oops. All right, keep it going like that. This ray here is definitely not going to converge with this one down here. Okay? They are definitely going in different directions, right? They are diverging. I'll go back now and sketch in ray number 2 just to see if we can't get a good set of rays here. Now notice that you don't need all 3 of these every single time. So let's do one here, like about there. Whoops. Well, my meter stick tipped as I was drawing that one. Let's try that again. It's going in, coming out. It's going like that. There we go. Something like that. Again, this one and this one are diverging. They're diverging away from each other. So the converging mirror converges for some of the time. But if the object is within the focal point, we have a problem. Okay? So remember what we did for the plane mirror. Now if my eye is here and I'm catching these rays as they are diverging and going into my eye, what do I need to do? Where is this image going to be? Think carefully. Let's do this. Okay, I am going to catch these diverging rays in my eye. My brain's going to say, where'd they come from? Imagine there's a point back here from which they all came. All right? So that means I'm taking this ray here and I'm going backwards to trace behind the mirror where I know there's no light here. Okay? Here's this diverging ray here. I'm going to take that ray and I'm going to trace it backwards. And I need a little bit more here. All right? I'm going to trace it backwards. Oh boy, I need to keep on going. Keep on going. Barely going to fit this one in. Woohoo, barely gonna fit it. In fact, I don't know if I'm going to. Just barely. Yeah, right here. There's a convergence right about there. Right at the edge of the screen. Cool. So, same with this one. This one here should be aimed right in about the same. Okay. Well, that one didn't come out quite so well, so I'm going to ignore that one. Point is that I have what I need here in order to figure out what the image is. The image is over here. This is the top of the image. Like so, where my axis is here. Like that. All right. Okay? All right, so what do we have here? Well, we have an image which is not the same as the image that was given by the converging mirror when the object was outside the focal point here. So let's start by answering the 4 image questions. What are the 4 image questions? First, we're going to start with, is the image real or virtual? Okay? So remember, behind the mirror is virtual space. In front of the mirror, where the light is real space. This is the real part. This is the virtual part. So this is a virtual image. It is created by our brain thinking about where this light looks like it came from. Okay, so anytime I have to dash these lines back in order to find an image behind the mirror, we're in virtual space. We're talking about a virtual image here. There is no light there. Okay, this is a virtual image. We can say that. I think you can see fairly easily this is an upright image compared to the object. That's an upright image. Its position seems to be fairly large compared to the object position, in addition to being behind the mirror. Okay, so the object distance, not the object distance, the image distance, sorry about that, the image distance, oops, sorry, I'm writing off the board here. Image distance is large, and when I say large, I'm saying large compared to the object distance, and it's behind the mirror. Okay, so it's large and behind the mirror. Lastly, I think we can safely say it's fairly well magnified. That's a large image compared to the object. Okay, so those are the answers to our 4 image questions. So it depends where your object is when you're dealing with a converging mirror. And you might be kind of concerned about why I call it a converging mirror in this case. Well, I call it a converging mirror because concave, you might want to say, oh, it's a concave mirror, and that would be perfectly true. But I have knowledge of what we're going to do next. And the next thing we're going to talk about is lenses. And when we talk about a concave lens does the exact opposite of a concave mirror. So that makes me confused. But a converging lens and a converging mirror, those two things do the same thing. So that's why I stick with the name converging mirror rather than concave mirror, because the words remind me that, oh, these two things do the same thing. Okay? Whereas concave do the opposite. And you'll just have to wait for that to see what I'm talking about. But nonetheless, a converging mirror, the image that you get from the converging mirror depends on where the object is. So if the object is out here past the focal point, then the ray diagram looks like the last one that we just did, where the image is flipped over, right, and is past the mirror on this side, on the real side. Whereas if I scoot the object within the focal length, now all of a sudden the image is behind the mirror and it's large and magnified. And you knew this already, I bet you, because if you've ever looked in one of those mirrors that for your faces, right, like a shaving mirror or a makeup mirror or something like this, right? You get, where do you have to be in order to get close up to it? You can get the mirror like right here. These are long focal length mirrors, so your head is within the focal point, right? Is inside the focal point of the mirror. So you're looking at a large upright version of your head, right? That's the image that you're seeing. So this works as a magnifier also if you scoot within the focal point. Alrighty. Good. So we've got one more ray diagram to do, and that's for the diverging mirror. So let's go ahead and tackle that one right now. I'm going to erase these ray things, but keep them in mind because we're about to use them again for the diverging mirror. All right, so the diverging mirror is the other side of the curvature, right? It's silvered on the other side. So now we're going to go here, we're going to do diverging. And we're going to have a diverging mirror which looks like this. And our symmetry axis, say, is, I always miss it here, it's about there. All right. Now, first thing to notice about the diverging mirror. Where is the center of the circle that is making this mirror, right? If I take my compass, right, and I'm gonna make my diverging mirror by doing this, notice it's gonna have to be over here. But note, the silvered side is this side, all the light's over on this side. So if the radius is over here, you know, the center and the radius over here, then the focal point is also over here. Huh, that's kind of weird, isn't it? Well, yeah, that's kind of weird. Let's just say the focal point is about here. Okay. However, we defined, right? We've defined the real side and the virtual side. Okay, so I want to make you aware, you could technically, and you could be correct if you did this, you could technically call this a virtual focal point. You would be technically correct. Because people nowadays have more of a meaning, they ascribe more meaning to the word virtual, right? But when this was first established, it was just a way of trying to say the light's over here, the light's not over there. Okay, so this isn't a side of the mirror, the light's not over there. Let's examine what happens when we draw the ray diagram for this thing. Here's my object here. I'll make it slightly taller this time. We'll go here. All right, so here's the object. And we're going to go ahead and draw the three rays for it. Ray number one. Ray number one. Good old ray one. God, I'm such a huge fan of ray number one. And you know, I think you will be too when we talk about some of the properties of ray one and what we're doing here. You probably haven't yet noticed the absolute awesome amount of information that ray one gives you, but you will. You'll notice. Okay, cool. So ray 1, we already know, comes in straight, right? Comes in parallel with the optic axis, and it goes out through the focal point. So what should we do? Well, I'm just going to draw this here, and doesn't the light just go like that? Well, no. It's a mirror. So it can't go that way. This is, by the way, a common pitfall. This is not a transparent thing. This is a reflective object. So there is no light going through the mirror. It's reflecting off the mirror. Remember? Real side, virtual side, right? Real's where the light is. So I have to have a different idea about how to draw ray number 1. Ray number 1, therefore, goes on the path that connects the focal point to where it hit the mirror, where the ray hits the mirror. So I'm going to take this, my ray hits the mirror here, the focal point is there, so I'm going to connect those two like that. And then I'm going to say, off it goes, right? It's as if, I'm just going to draw this in here, I'm just going to dash that in, and then off it goes that way. So ray number 1 goes like in, out, but it comes along the path right here. Okay, it comes along that path. Ray number 2 is just ray number 2. Ray number 2 is, ray number 2 never really changes. Ray number 2 is always the same. Okay, which is cool and also, whatever. Ray number 2, you always know what you're getting. So here we go with ray 2. It's going to hit this point here. It's going to come straight out at the exact same angle that it came in at, which would therefore put it approximately through here, I think. Oh, that's on the outside. Again, I'm not taking real care with the angles here, but it looks close enough for government work. Now, just to be sure, you only need 2 rays, right? Because as soon as I look at ray number 2 here and ray number 1, I can see they're diverging. Well, duh, it's a diverging mirror. Of course they're diverging. Well, wait a sec, hold on. In the converging mirror, I got diverging rays. Yeah, that's pretty cool, right? Rest assured, you do not get converging rays with the diverging mirror. It does not happen. So I take a look at these 2 rays here, and they're going like this, right? So it's like, hey, where'd they come from? Now, I've already cleverly traced back ray number 1. Ray number 1's already along that line just to convince me that I'm on the right path to draw ray 1. So I've already put ray number 1's back dashing in here, right? Ray number 2, I can do that now. Ray number 2 I've got here, which would go backwards and be about there. So I'm going to say it's going to hit there. Let me just draw ray number 3 real quick before we lose our focus on this one. Remember, ray 3 goes through the focal point or from the focal point, but at least it's aimed at the focal point. So in this case, ray number 3 leaves the top of the object and is headed directly at the focal point. It's headed directly at the focal point, like that. That is ray number 3 right there. Ray number 3, however, never reaches the focal point because it hits the mirror and reflects off before that ever happens. But we know that ray 3 reflects off, since it's aimed at the focal point, it reflects off parallel with the axis. So that means ray number 3 comes off like this. Oh, that's beauty. And I can trace it back. And, ooh, that one worked out real nice. A little bit of care in that one. So there's ray number 3 traced back. It's hitting my image point right there. So the image is right here. There's the image. Okay. Alrighty, answer the 4 image questions. Do them right now in your head before I do them. Otherwise, if you're not one little step ahead of trying to answer these questions, then what do I say? Then you gotta try harder. How about that? 4 image questions. Do we have a real or virtual here? Hopefully reasonably straightforward to see this is a virtual image. Again, upright compared to the object. When I look at the image distance, this is much closer to the mirror than the last one I drew, which was way over there, like about a country mile. So in this case, the image distance is smaller than the object distance. But it is still behind the mirror here in virtual space. So we still have that. I'm going to write it smaller. When I say smaller, when I say large or small, I mean in comparison to the object distance. Smaller and behind the mirror. And I think you can relatively say that, I think you can relatively safely say this is a smaller image in exactly the same way that the other one was bigger. Right? That image was much bigger than the object I drew. This image is much smaller than the object I drew, and therefore we would say it's minified. It's not magnified, it's minified. I do not actually know if that is a standard terminology, but we're going to go with it because I like it. And if I like it, so do you. There we go. Answers to the 4 image questions here. So we have gotten a virtual image from a plane mirror, we've got a virtual image from a converging mirror, and we've got a virtual image from a diverging mirror. Okay, know how to draw all 3 of those and how to distinguish between them. We've also gotten a real image from the converging mirror. We will never get a real image from a plane mirror, and we'll never get a real image from a diverging mirror. So apparently the real images are kind of the exception in the mirror case here. All right. Good. So those are the ray diagrams for the salient situations where I have either a plane mirror or a curved mirror and an object distance, which depends on relatively where it is located with respect to the focal point. Okay. Now let's get on to doing a little bit of, oh, and by the way, please become very familiar with these ray diagrams. Okay. Now, I'm sketching these out for you now. I do expect you to practice these things. Not every problem is going to be as straightforward as just having one mirror and boom, boom, you're done. Okay, what happens if we have 2 mirrors? Okay, now what happens? Okay, so practice working on extensions of this, right? Especially next week when we get into lenses, and then we're going to start talking about what happens when we have a lens with a mirror, or 2 lenses and then another mirror, right? When we start putting this stuff together to make an actual instrument, you have to be able to rely on the principles of use established when you're doing the ray diagrams, so that you can feel confident about the rays that you're drawing and feel pretty good about the image when you locate it. Okay. Okay, so what I'd like to do is go back to the converging mirror, mostly for its ease, but could use anything, I suppose. We could use anything, but what I'm going to do is I'm going to take a look at this, and I'm going to say, all right, here's my converging mirror again. I want to draw rays number 1 and 2. I'm just going to sketch this out really quickly. Here's, let's say, my focal points here. And I have an object here. Let's put it here. Actually, I'm going to scoot it a little further out than that. Let's scoot it a little bit further out. Let's go for here. Okay, object. I'm going to draw rays 1 and 2 for this right now. So ray 1, I got grid lines, so all I got to do is make ray 1 straight along that line there, coming in that way, and then dropping through the focal point this way. I could be a little bit more careful with this. So let's go ahead and sketch ray 1 coming out, going through the focal point here. I'm going to make it really a really extended line here. And so this is ray 1 as it leaves, and ray 2 we have by going here to here, and on the in, and now on the out. I think I want to go about there. Like so. Oh shoot, I did not get that on there really well. Let's try again. There we go. Okay, so that's ray 2 on the out right there, and that's ray 2 on the in. Okay. I mentioned before we love ray 1. Why do we love ray 1? Examine what happens when I move the object around. How does ray 1 change? If I take the object and I scoot it way in here close to the focal point, what's different about ray 1? Answer, nothing. I take the object, I scoot it way back over here. What's different about ray 1? Nothing. So, this is why we love ray 1, because we're guaranteed, now this is for a situation here with the converging mirror, where I have the object outside the focal point, okay? By the way, this is true for not just this situation, but it's nice to see it in this situation. That guarantees us, here's ray 1 leaving the mirror here, that guarantees us that the image is somewhere along this line, because what we're doing is expecting to see an intersection of another ray with the ray that is leaving the mirror from ray 1, right? So in this case, I see it connecting here. But if I had scooted it way forwards, then notice that this angle would be much steeper, and it would have gone way over here. But the image is still on this line somewhere. So once you draw ray 1, you feel good. And you would note the same thing with the diverging mirror when I trace that little leg between the focal point and where the ray hit the mirror. The image has to be in there somewhere. That's ray 1. So ray 1, the reason we love ray 1 is because it tells us, hey, the image is along here somewhere, right? So it narrows down the, oh my gosh, where's the image, to, it's got to be along this line somewhere, okay? And that helps your, it's like a checkbox in your mind, right? It helps your conceptual understanding, because now you go, oh, I've got one of these images, it's over here, I can see it, it's on this line somewhere, okay? All right, so in this case, my image is here, like so. All right, now what I'd like to do is, since I'm going back to this case, this is going to be the translation of the ray diagram into mathematics. What we're going to do right now is take this and make some math appear out of nowhere. All right, so let's make the math representation. I am using the word representation intentionally because, well, you folks are in 4C now, so you should have a pretty reasonable handle on this, though perhaps it's never been done for you explicitly. The idea of physics is to look at multiple representations. Okay? This is one representation. It's a diagram. It's a pictorial representation. Now we're going to take this this thing, this physical situation, we're going to translate it into a mathematical representation. What other types of representations are there? Text, right? There's words. I can describe to you, hey, I've got an object outside the focal point, and the light's going to hit a converging mirror. Okay, boom, here you go. That's this right here. Okay, so there are different representations as you go along, and learning to translate between those and understand what the important points are here, which I'm going to make sure I represent here, which I'm going to make sure I represent here. Okay, that's a really useful skill to start developing, and ultimately continue to develop as you go along in doing whatever it is that you're going to go do. Let's make the math representation. This is called ray optics, but it also goes by the name of geometric optics. So we've got some geometry to deal with. Why? Because we've got angles. The law of reflection is all about angles. Okay? So let's take a look. I have some angles that I know are the same. Specifically, ray 2, right, has equal angles. It's right as part of the law, right? So this angle here, I don't want to use that one. Give me this one. This angle right here, let's see, can you see that? Yeah, is going to be equal to, I'll put it way over here, this angle there. Those two angles are the same. No, that one you can't really see too well. Well, the point being here, maybe I'll go over here. This angle here, there you go, that one should equal that one. Is that better? Yeah, that's a little better. So we'll put that cute math thing where you put a one diagram, one bar through each one. Yeah, these are equal angles, right? Because ray 2 is, by definition, the one in which those angles are equal. Okay? So, and right, it's the normal right here. So what I have is the ability to then look at, okay, if those angles are similar, if those angles are equal, then I should have triangles that are similar. That's what I wanted to say. All right, so if these angles are equal, this is theta I and theta R. Since theta I and theta R are the same for the ray 2 case, what I'm going to do is say then these tangents are the same. Tangent theta I is equal to tangent theta R. Hopefully you would agree with that. Sorry about the glare, but it just says tangent. Which means that I want to look at the triangles that these rays make. So what I want to do is look at, let's see if I can outline it here. I want to look at the triangle here, along here, all the way through, and then back along the ray. Can you see that triangle? This one. Yeah, that triangle. That triangle should be similar to this one here. I'll do, let's see, I got to do a slightly different cross-hatching to it. Maybe like that. That triangle should be similar to that triangle. Ooh, tougher to see that. But nonetheless, it's there. All right, this thing has a side, which I'm going to call the height of the object, right? This is the object right here. So I'm going to denote a couple of things here. Object height and image height. I'm going to call that H with a O and H with an I. Object height and image height. Now, I'm also, since tangent involves the opposite and the adjacent, I need a name for the line, this blue line, the long side over here. That's basically, we've already talked about this, yeah? That's the distance from the mirror where the object is. So this is basically the object distance. The object distance I'll call DO. And the same thing's true with the image. The image is a certain distance away, and that's part of the triangle, and that's going to be DI. All right, so this thing here is HO. This thing here is HI. Now, the commonality of the axis here kind of prevents me from saying, oh, look, that side is DI and that side's DO, but hopefully you can kind of see it. The side that goes from here all the way in, that's the object distance, DO. The side of the triangle here that's more heavily colored in is the image distance, that's DI. So the what do you call the base of the triangle, I guess, maybe? If this is the base of the triangle, that would be the image distance. Okay? Since the tangents are equal, then the ratios of those sides is also equal. The ratio of those sides is equal. So the tangent of theta I is going to be the incident angle. So that's object height over object distance, and that should equal image height over image distance. All right? Okay? All right, sound good? Hopefully. Similar triangles. Now that I have completely kind of colored in this one, I need to use ray 1 and find that one's similar triangles. So, down here I'm just going to make another sketch of ray 1 coming in and coming out by itself, so we can just see by looking at ray 1 what the similar triangles are going to look like. Alright, so let's take a look here. Okay, so ray 1 looks something like that, and the image was somewhere in here. This is the focal point here, F. So the image was somewhere here. This is object. This is image. Okay, so the image is somewhere in there. So what we have now, notice, is that the reflected ray crosses the axis and makes parallel angles. In other words, these two triangles here are going to be similar because those angles are the same, right? This angle here, and therefore this triangle here, that triangle there, and this triangle here, those two triangles are going to be similar. Similar. That pen, triangles. Similar. Similar. Huh, this pen's having trouble spelling. Same deal though, right? Same deal. The angles, these are parallel angles. Therefore, the tangents of those angles are also equal. Okay. Now, if you're sharp-eyed, you notice I'm glossing over a small approximation, which maybe I'll tell you about. But right now, check it out. Same reasoning. It's not theta I and theta R anymore, but it's the thetas that are parallel on either side of the focal point. Okay. The tangents of those angles must also be the same, but notice then that the height of the triangle here is the image distance. That's the image distance for this thing here. And the height of this triangle is the object distance. It said distance. Dang it. The height of the image is the side of this triangle, and the height of the object is the side of this triangle. That's what I was trying to say. Okay? Because look, that's a parallel ray right from the very top of the object straight into the mirror. So this thing here must be height of the object. Okay? So I can do the same basic thing. I'm going to relate the tangents of those angles. we'll do this, and I'm gonna, well, maybe I can just, can I sneak it in right over here? I can do the tangent, I don't know what to call them, theta 1 and theta 2. Is that still on the screen? Okay, good. So whatever they are, theta 1 and theta 2, all right? So in this case, I'm going to do the opposite over the adjacent, right? So for theta 1, the opposite is the height of the object. The adjacent is the focal length. For this triangle right here, that's the focal length, is the adjacent side. We'll call that F. For tangent of theta 2, over here on this one, the opposite is the image height. Okay? And now, it's really just this piece right here that I want for the, right here. It's really just the darker top line right there. That's what I want. Because that's the adjacent side to the angle of that triangle. So, I know that the image distance is the distance from the image to the mirror, and I know that the focal length is the distance from the focal point to the mirror, and fortunately, if I subtract those two things, I'll get what I want here. So this has to be image distance minus focal point. Right? Can you see that that's the dark top of this triangle right here? Is the image distance, which is the entire thing, minus this little piece right here. That gives me that piece right there. All right? So, translating this into a cohesive piece. All right? I've got this piece from array 2. I've got this piece from array 1. I can connect these two things, yeah? Because if I form the ratio of image height to image, if I form the ratio of image height to object height, in other words, I form image height divided by object height, right? I'm going to swing that thing underneath. I'm going to pop the DI over there instead, okay? And I do the same thing over there. Well, I'm just going to equate those two things, and we're going to come out with something that is going to relate all of these distances along the axis, because notice everything else is related to the adjacent side, which is located along the axis. It's these distances right here. So we're going to get a relationship which relates how far away is the object, what's the focal length of the mirror, where's the image distance. And this will be able to tell us. Okay? So that's our goal. Quick little algebra interlude right now, and we'll figure it out. So we'll do that over here. Okay, I'm going to form HI divided by HO, which means I'm popping that thing under there. Same deal there. I'm popping that thing under there, and then I'm going to flip over what the other things are. So I'm going to have HI divided by HO equal to DI over DO. That's this piece here. That one over there is going to be HI over HO, okay, equaling DI minus F over F. Since those two things are equal, then the right sides of those are the same, so I should just be able to say that they're equal to each other. And so what I'm going to do is just take that and put it right over here and say it's equal to DI over DO. Alrighty, and now let's just solve to come up with a relationship between the distances of the image and object and the focal length of the mirror. In order to do that, I'm just going to go ahead and divide this side. Right, I've got a denominator here which I can just separate out. So I'm going to do DI over F minus 1 equal to DI over DO. Pretty cool. How about I flop the 1 over to this side, make it plus 1 over here, and then I divide everything by DI. So that takes out DI here and sticks it underneath this thing. So what that gets me is 1 over focal length equal to 1 over object distance plus 1 over image distance. And this thing right here is the representation mathematically of how to locate an image based on knowing the focal point and where the object is. Okay. Since these ray diagrams all involve triangles that are similar, then this must be the relationship that falls out that connects where things are relative to other things. All right. I have 2 pieces to talk about, and I forget how much time we have because we had to start a little bit on the over side, but a couple of minutes. Okay, so here's what we'll do. I mentioned before that I snuck an approximation in there. I'm not going to talk about that today. Maybe I'll talk about it tomorrow. I want you to see if you can find it. Okay? Hint, it's in this one. Okay? The second one is we need to come up with a sign convention. Okay? Because remember, we've divided the mirror into real and virtual sides. So I need to be able to distinguish between those two things. Okay? So let's call everything that happens on the real side positive. Right? Because that's where light is. Let's say everything that happens on the virtual side negative. Okay? Because why not? All right? That means then that I'm going to inherently start ascribing positive and negatives to real and virtual images. Okay? And the same thing's true with the object height and the image heights. I'm going to call an object, I'm going to call the object height positive, because I always draw the object above the axis here. If I get an inverted image, then I'm going to call that a negative height. All right, so there's 2 things right there that we're going to do to help our mathematical representation of where things are, because we need to know, is it above the axis or below the axis, and the plus and minus is going to be able to help tell us that. Is it in front of the mirror or behind the mirror? Plus and minus to be able to help tell us that. All right? Okay, I think I am out of time now, so I'm going to leave you with that. We will pick up tomorrow with a couple of demos on how that works and how to use that, and be informed by what your ray diagram is telling you. Okay? So until then, I will wish you happy rest of your day. Get started on some of the homework questions that we've got going, and take a look at the PLC for this week. Alrighty? So for now, I'll say happy rest of your day, folks. See you later.